Hello everyone, myself Gaurav Bhattana, Assistant Professor of EC Department at LJ Institute of Engineering and Technology. In last session, we have finished unit number 2, that was orbits and launching method. Today, we are going to start unit number 3 as per the GTO syllabus, that is the geostationary orbit. In this session, we will cover introduction, that is a definition of geostationary Earth orbit, then radius and height of GEO, and the loop angle. First, we are focusing on the definition. That means, what do we mean by geostationary satellite? It is a satellite in geostationary orbit that appears to be a stationary with respect to the Earth. Hence, its name is geostationary. For the satellite to be a geostationary, there are total 3 conditions are required for an orbit to be a geostationary. The first condition is satellite must travel eastward at the same rotational speed as the Earth. That means a rotational speed of satellite should be same as the rotational speed of the Earth. Okay. Second condition, the orbit must be circular. That means its shape should be a circular. How it can be possible? As the geostationary orbit lies on the equatorial plane of Earth. For that, the value of eccentricity will be a 0. As we have seen in the Kepler's first law, that if the value of eccentricity is 0, then orbit must be a circular. Okay? If the orbit is non-circular, then the value of eccentricity lies between 0 to 1. Or you can say elliptical orbit, right? Third condition, the inclination of orbit must be a 0. Inclination, that means the inclination angle. The angle between equatorial plane and the orbital plane must be a 0. How it can be a 0? Because the orbit of geostationary lies on the equatorial plane. So the angle will be a 0. Because the orbital plane is same as the equatorial plane. Right? Now, what is the radius and the height of GEO? As per the Kepler's third law, which is used to find the radius of the orbit, for circular orbit, the semi-major axis is equal to the radius, which is represented as AGSO. Over here, A stands for radius and GSO stands for geostationary orbit, right? Then, as per the Kepler's third law, that is A cube is equal to mu upon n square. Over here, A is semi-major axis, n is the mean motion, and mu is geocentric gravitational constant. So, we know the second equation, that is capital P, that is orbital period. is related with the mean motion. Capital P is equal to 2 pi upon n, right? So, based on these two equations, we will get this equation. How? Simply place AGSO instead of A. So, AGSOQ is equal to mu upon eta square, but the value of n is 2 pi upon P. Okay? So, 2 pi upon P square stands for 4 pi square into P. So AGSO is equal to mu P upon 4 pi square raised to 1 upon P. Okay. So the period of the geostationary is 23 hours, 56 minutes and 4 seconds, which is calculated with the help of by putting the value of geocentric gravitation constant over here and the period for the geostationary, which is the time taken for the Earth to complete a one revolution about its north-south axis, which is measured relative to fixed time. So, the period is equal to 23 hours, 56 minutes and the 4 seconds. So, first we need to convert this unit into second. Okay, because the unit of period is second, right? So we will get the value of a radius of geostationary orbit is 42,164 kilometer. Now, based on this equatorial radius of the Earth, which is 6378 kilometer, AE. Over here, A represents radius, E stands for Earth, that means radius of Earth is equal to 6378 kilometer. We know that. Based on this value, radius of geostationary orbit and the radius of Earth, we will get the height of geostationary orbit. How? By placing this formula. Height of geostationary is equal to radius of geostationary minus radius of Earth. We know the value of radius of geostationary orbit is 42,164 kilometer minus radius of Earth, that is 6378 kilometer. Then we will get the height of geostationary orbit to be 35,786 kilometer. Okay. See, this is the practical value of height of geostationary orbit. Ideally, we are taking it as a 36,000 kilometer. Okay, so this is the radius of geostationary orbit and this is the height of geostationary orbit. Okay. Okay. Now, the next topic is antenna look angles. First of all, what do you mean by look angles? Look angle for the ground station antenna are azimuth and the elevation angle, which are required at the antenna. Why? Because it has to be points directly at the satellite. The value of these two angles, azimuth angle and elevation angle, changes for the non-geostationary orbit. But the value of these two angles remains fixed. It doesn't change for geostationary orbit because The satellite present in geostationary orbit appears to be stationary with respect to the Earth. Okay, so first of all, we need to know about that what do you mean by azimuth angle and the elevation angle. Why? Because these two angles are helpful in order to point at the satellite directly from the Earth station antenna. In which direction that I have to point my Earth station antenna such that I can get a maximum gain from the satellite, right? So, we are first focusing on the azimuth angle. Now, the azimuth angle means the angle between a local horizontal plane and the plane passing through the Earth station, satellite, and the center of Earth is called azimuth angle. Okay? In simple terms, measuring the horizontal angle at the Earth station antenna to the North Pole. So this angle is called azimuth angle. Azimuth angles are actually the horizontal angle, right? Which is used to track the satellite horizontally. Okay? And second one is elevation angle. So the elevation angle is the angle between the vertical plane and the line pointing to the satellite. So this angle, this is the ground level and this is the line pointing the satellite. So this vertical angle is known as the elevation angle, which is perpendicular to the horizontal plane. So the measuring the vertical angle at the Earth station antenna from the ground to the satellite is known as the elevation angle. Okay. So these are the two angles, azimuth and the elevation angle. So actually the antenna loop angles is a brief theory about how to point a satellite and antenna at a particular angle. So how it can be done, that we will discuss it onto the next lecture. These are the references. Thank you.
So I'm going to summarize the session that first we have seen what do you mean by geostationary orbit, what are three different rules for geostationary orbit, like orbit must be circular. Second, its inclination angle should be 0. Third, it rotates at the same velocity as the earth rotates. So based on that, we can see that our satellite will looks like a stationary if I can view on a specific point from the surface of the earth. Apart from that, we have also seen that the radius of geostationary orbit is 42,164 kilometer and its ideal height of geostationary orbit is 36,000 kilometer. But in the exam, you will find that calculate the actual height, or you can say a practical height of geostationary orbit, that is 35,786 kilometer that we have already derived. Okay, and The third and the most important part is the antenna look angle that we have seen. We have seen the definition of elevation angle and the azimuth angle. So in the exam, you have to calculate the azimuth as well as the elevation angle. Azimuth angle is horizontal angle and the elevation angle is vertical angle. So in next session, we will see the different formulas to calculate the antenna loop angle, like a specific formula for azimuth angle as well as for elevation angle based on the specific position of satellite as well as the latitude and the longitude of Earth station. Okay, thank you once again.